To build a modern application like Netflix or Instagram, your system has to process millions of massive, high-definition photo and video uploads every single day. If you try to force a huge 4K video file directly into a traditional relational database, the system immediately starts to break down. Relational databases are optimized strictly for structured alphanumeric strings. An unstructured raw binary media file is entirely incompatible with this rigid row and column architecture. Forcing this fit bloats the database size, slows daily backups, and obliterates memory caching, bringing response times to zero. To bypass this bottleneck, software engineers developed an entirely different storage architecture, the Multimedia Database Management System. Scaling a media-heavy platform requires moving away from the limits of rows and columns to an architecture built specifically for high-density binary data. When a user hits upload on a massive file, we have to determine where that data physically goes. Looking at this diagram, we see the first approach, the blob, or binary large object. The system converts the media file into a raw binary stream and stores it directly inside a database cell. While this keeps everything in one unified location, trying to pull gigabytes of raw binary out of a database cell during heavy user traffic creates severe performance bottlenecks. The modern solution is the pointer system. Instead of storing the heavy file internally, the video is routed to an external distributed content delivery network, or CDN. The main database table receives only a lightweight URL pointer, remaining fast and responsive. In cases where files must be stored internally, tools like MongoDB's GridFS manage the massive size by slicing the video into smaller individual chunks and distributing them across multiple document collections. Decoupling the massive binary payload from the database's organizational logic ensures that platforms can support millions of simultaneous users without collapsing under the sheer weight of their own media. Once the file is safely stored, we run into the next logistical hurdle. How does a database, which processes text and numbers, actually comprehend the contents of a binary video file? The system first categorizes the data by its time dependency. Static media, like a photograph, is processed instantly. Dynamic media, like a streaming movie, requires specialized time indexes. The database dissects the file into 3 layers. The bottom layer is raw media data, the physical ones and zeros. The middle isolates descriptive metadata, alphanumeric tags like file size and date. The top extracts structural features, mapping physical traits like color histograms. By separating a single upload into these 3 distinct layers of metadata, the system translates a dense block of binary noise into a highly structured, mathematically queryable asset. A database that can store a file but cannot describe its contents creates a new kind of bottleneck. This is bypassed through content-based image retrieval. The database uses algorithms to scan the actual visual elements of the image itself. When a user uploads a reference image to run a search, this diagram shows how the system analyzes the new image's matrix. It calculates texture maps and color histograms to find an exact visual match. The same logic applies to audio files through acoustic profiling. The database indexes frequency distributions and pitch metrics, finding a matching track without knowing the title. These feature profiling capabilities, built into tools like Oracle Multimedia and MongoDB GridFS, are the exact mechanisms powering the reverse image and audio searches we use every day. Multimedia databases function as intelligent engines that mathematically parse the visual and auditory textures of the digital world.